It's a rainy day, radio fans, and in the ham shack making and testing an RF transformer on a toroid core. Purpose of this transformer is for the input of the 3-400 amplifier I'm building. Going to build it in the tube tester cabinet. Just put RF enclosures and connections with it. And this transformer thing is a little messy. It's all about the core, mainly. And we don't know much about the cores. These are Amadon T140-67 cores. The A sub L value is supposed to be 45, and I measured it at about 150, so I don't know what's up with that. This is to be a 50 ohm primary and about 110 ohm secondary to match the about 110 ohm resistive input on the tube. And been looking at methods and calculations from this book by Kiekkerts, Kiekkerts, called RF Electronics, and show you some other sources for information, especially Amadon on the cores. This is a classic document from Amadon, iron powder and ferrite coil forms, available on the internet. And it gives information on the different types of materials, either iron powder or ferrite, and formulas for estimating the inductance per turns. I found that it's got to be wound and tested because the data just didn't match the core. Very important, see the page on power considerations, because I burned one of these cores up and it really stinks up the room. So there are recommended AC flux density limits per frequency. And there's a formula in here for calculating flux density. Real simple math. So pick a core material for frequency. They suggest iron powder for higher powers, but the ferrites have higher permeability, which means fewer wire turns and less wire loss. And I'm finding that wire loss makes quite a difference. And here's a real good paper from one of the inductor companies. I think it's Micrometals. It's design-toroids.pdf, and it gives equations for, that's the flux density, and that relates to the losses. So some explanation on how transformers work. And then ferromagnetic core design and application handbook. And that's by Doug DeMaw. That's also available online, and this is a complete book on the topic with some blank pages. So anyway, there's that. And here's a web page I saved from Micrometals, powercores.htm, which goes over core losses. Very important. There are also wire loss. That's wire resistance, skin resistance, and the inductance of the wire makes a difference. In other words, the diameter of the wire. But besides the Amadon data on the cores, this is the best I've found on the transformer. It's from the book RF Electronics by Kiekkerts, Kiekkerts, Chapter 3. And Chapter 3 goes into detail on how to calculate the transformer if you know the characteristics of the cores, and using the geometrical mean distance to calculate the center frequency, center impedance, which is actually resistive, not impedance, and gives an example of transformer design. His statement that the leakage inductance is a thousandth is suspect. What I'm finding is that L sub M and L sub S in my transformer is only off or different by a factor of 4 or 5. So, but this shows how to calculate the inductance of the windings and find the frequencies related to the transformer. And note these are known as broadband transformers. And so I'm trying to get a transformer that's at least broad enough to cover the entire 75 and 80 meter band, maybe even into 40. So there are the documents to read to understand how transformers work. Unfortunately, it's nearly impossible to go make one from this information, so I'm going to show you how to do that. So unfortunately, or fortunately, however you look at it. This document's nice. This document is accurate except for his statement that the L sub S is typically 1,000 times larger. I found the inductance in this transformer of something like 4.3 versus about 1.6 microhenry. So, but he's making a bifailure transformer, much different animal. I'm making one here for power application. So like Kiekkerts says, you got to make a test winding, and that means a test transformer. And this is my test transformer. It's actually, I started with putting about 10 turns primary and secondary on, and just checking the frequency response with an RF generator. And then I used the sweep from the generator out to sweep the scope, and I could see the passband on the scope display, and I'll show you that here in a bit. But what works almost as well and is better at showing how flat the passband is this microwave RF detector probe I made and a good 3-place voltmeter. So get a core. This is a T140-67 from Amazon, and I put 5 turns primary and secondary, and it came out to a nice flat response across about, well, pretty much 80 to 40 meters. This one's made with 14 gauge uninsulated wire, and this is made with 16 gauge insulated wire with polyimide tape around the core. So got better bandwidth out of this one with the thicker wire, but that's what we'd expect. There's less losses. And here I've measured with the detector probe with a capacitance and a primary of the test transformer and with no capacitance, and recorded the primary and secondary voltages. And you can see that they're roughly the same. 3.5, 3.8, 7.3 megahertz with a tuning capacitor and primary 0.654, primary 0.773 secondary. That's for a 1-to-1 transformer. Then without the capacitor. The capacitor is used in the primary of the transformer. I used a 825 picofarad mica and put it in series with the primary with a 50 ohm resistor to make the primary resonant. And there are 2 tests with the capacitor and 50 ohm resistor in the primary, and that's a primary with the connector that goes to the RF generator. Then the secondary is opened, then it's shorted, and the open case gives the L sub M, the mutual inductance, and the L sub S with the secondary shorted gives the essentially loss inductance. And those 2 inductance values resonate with that capacitor at 2 different frequencies. And that allows at each frequency with the primary open or shorted to calculate the effective inductance looking into the primary with the secondary open and the secondary shorted. And with the secondary open, that's the low frequency inductance. And with the secondary shorted, that's the high frequency inductance. And the high and low frequency inductances are then calculated to find the frequency where their reactance is the same as the system, which is 50 ohms. So take the high and low reactances, or the high and low inductances, find a frequency where the inductive reactance is 50 ohms, and those are the cutoff frequencies. And this is what means cutoff frequency. This is what the passband looks like on a sweep from 100 kilohertz up to 14 over 15 megahertz. And the cutoff frequencies are these 3 dB down points from maximum. And with a capacitor and a primary and a 50 ohm load resistor, this passband is astonishingly flat. I calculated that passband is flat within 1/4 of a dB, which is just an amazing figure. The flatness, 3.5 to 4 megahertz and 7.0 to 7.3 was 0.256 dB, and on 40 meters it was 0.085 dB flat, and you can't get that kind of flatness from an LC network. That's absolutely perfect. So the square root of those two frequencies multiplied together gives the center frequency right there. Now the performance of the transformer is not as good with the capacitor and resistor in the primary. But what's really interesting about this is that one-to-one transformer can be used as an inductor with a secondary shorted and tune the primary, and you get an inductor, believe it or not, whose reactance goes down as frequency goes up. And that resonant circuit is just absolutely dead flat. So there's a way to make a special kind of L network that's tunable with just an air variable capacitor. Or across that frequency range, you don't need to tune it. Testing, here's testing at 3.5 megahertz, a 2 volt peak-to-peak input. And just put the RF probe across the primary here. And 0.81 volts reading on the RF probe and meter. Primary and secondary RF voltages are read on the meter. Then the transformer is taken off, and that's replaced with a 50 ohm dummy load and an RF BNCT, and that's put in the generator. And then that open port is measured with the RF voltmeter to get a comparison of what the generator output reads with a pure 50 ohm load on it, which is 0.841 volts at 3.5 megahertz, versus with the transformer on is 0.777. So the transformer is not purely resistive, but that gives us an idea of how much. Now with the RF generator set to sweep from 1.6 to 6.2 megahertz, somewhat arbitrary. You see the sweep pattern on the scope here, which is not synchronized, but you can see it's a trapezoidal shape. That's not flat. It was much flatter with 16 gauge wire or 14 gauge wire than it was with 16. But that's also an somewhat unreasonable bandwidth. I just want this for 80 meters. Well, here's the primary response looking at the generator on the frequency span from 3.5 to 7.3 megahertz, which is the amateur band. And from those measurements, you can get an idea of the voltage change and calculate the dB, the decibel change. That's on the primary there, so let's move the scope to the secondary. And with the scope on the secondary, and a little difficult to see, but there are two brown tubular 50 ohm resistors. Let's get them around so you can see them. Right there. Those are 50 ohm resistors soldered in series to make 100 ohms, which is approximately the input resistance that the tube amplifier will have. And the scope sweep is quite a bit flatter. Not ideally flat, but that is about 0.2 of a volt change across that step right there. So 0.2 of a volt out of 1 volt from 0 to peak. So 0.2 out of 1, you can use that in a dB voltage calculator to find the change in dB across that winding. And then if we change the span to 4 megahertz across the 75 and 80 meter band, we see it's almost dead flat. So that's the goal. That's really what I'm after. I'm not really after getting a transformer that's several bands wide. Why use a transformer instead of an L network or a so-called external tuner? Well, IMAX says that an external matching unit, there's no such thing as a tuner, can be used, but amateurs make the mistake of trying to use a piece of coax between the tuner and the amplifier, and that's a disaster because the coax is 30 picofarad per foot. Matching network has to be put right at the input of the amplifier, not somewhere else. So this is small enough to be put right in between the connector and the tube socket. So very little stray capacitance. The second benefit is DC voltage isolation. All these tubes being used are 40 to 80 years old. And the older they get, the more they tend to have internal gassy leakage. That leads to arcing. If there's an arc over between the plate and the grid, then that destroys the exciter. And I've heard a couple people on HF say they lost a transceiver because an amplifier flashed over. So this will give especially with this wire, and that wire has insulation good for probably 500 volts. And that polyimide tape is good for, I think, 4 kV. And the core also has DC voltage isolation. That pretty much guarantees that if the plate shorts over to the grid, then the high voltage can't go to the exciter and destroy the final amp in the transceiver, which would also destroy the input of the receiver. Arcing, dead amp. Gotcha. Arcing is an RF phenomenon. According to one of the original research papers, electrical arcs tend to have frequency components up in the megahertz range. This transformer is a bit above that. It starts rolling off quite a bit at 1.6 megahertz, so that will tend to reject arcs. And another safety factor is that a sudden, very high energy transient, at some point this core won't pass it because when the core saturates, it opens up. So major safety is included by using this transformer instead of a L network. And I was going to make an L network with an inductor using this core anyway. So this, instead of the L network, just saves having a capacitor. And when I rewind it with 16 gauge wire, it'll be dead flat across the band that I want. So in a nutshell, read those sources and understand what they mean, but there's no way to do this without winding and testing. If you don't have this highfalutin test equipment, get a $30 sine wave generator out of China for 20 to 50 bucks. A kit, build a kit, and a modern digital storage scope that's more than good enough for this is $300. This was a $2,200 scope back in the early 90s. This is a special scope. You don't need that for this because this is a characteristic 50 ohm system. That's a very high resistance input scope. So these modern digital storage scopes with if they have 50 ohm inputs, that's ideal for this. And pretty much any voltmeter will work. You don't need this $600 unit. Make this RF probe. I have a video here on this channel how to do it. A microwave surface mount diode and some container to put it in. Real easy. And here, about a foot of the RG174 is the output capacitance. So there's no capacitor in there. And for a resonance test, that's all you need. And from resonance, you can calculate the windings. LCR meters don't do a very good job of that. For inductance, you'll need an LCR meter to measure the capacitance of the capacitor used to resonate the windings. You got to have one or the other, an accurate value of capacitance or inductance. But this low microhenry was not able to be measured accurately with my LCR meter. But the ultimate test is a ham transceiver. And I'm getting ready to modify this 50 ohm dummy load to be a 110 ohm dummy load, which will simulate the input of the amplifier, and I'll drive it full power, which would be used to excite the amplifier. But if you have a transceiver like that Yaesu 857, which has adjustable output power, then you can turn the power way down to a couple watts and use that for an RF source. And especially that Yaesu because it's broadbanded. So if it's not broadbanded, you can only test in the amateur bands. Since we can't transmit anywhere else, then that's all we need. Except for the one last reason for using something like this on an amplifier, and that is for reducing harmonics. This transformer will pass the second harmonic from the exciter really well. This one will start rejecting it. So if I'm transmitting on 75 or 80 meters, that one with a 16 gauge wire instead of 14 will start attenuating the second harmonic near 7 megahertz and pretty much cut out the third harmonic on 20 meters. So that means that there's less harmonic content going in the amplifier, so there'll be less coming out. Because the amplifier is very broad-banded, it'll amplify the harmonics also. So another reason to do this. But takes a little elbow grease, a little experimenting to get it right, but that's what amateur radio is about radio experimenting. So get you some cores and some wire and have fun with that. And to explain the testing with a schematic, here's the RF source here. 50 ohm resistor. Pick a capacitor that is resonant with about 1 to 10 microhenry in the HF range. I used an 820 picofarad mica because they're stable and precise. And a transformer. Start with 5 or 10 turns, primary and secondary, then short the secondary. And this is a configuration that gives an extreme flat bandwidth. But find a resonant frequency where the voltage across resistor is maximum with the RF probe. Then get the formula for frequency, which is that, and transpose it to find for L, which is 1 over omega squared divided by C. But it's good to practice the algebra. Then once you find the inductance, say it's 1 microhenry, then do the inductive reactance formula, which is two pi FL, and transpose that to find, or correction, as it is, a 2 pi F times the inductance that was calculated from the resonance formula, and use that to find the frequency. So X of L over 2 pi L gives a frequency for the high frequency cutoff. Then open the secondary here. The dot represents a solder joint. Open the secondary. I calculated about 4.2 microhenry. And do the same thing to find the 50 ohm frequency with the secondary open, and that's the lower cutoff. Then that can be used to calculate the center of the passband response. But this is all better off tested. But it's really good to learn to do this and learn to do the math, because the math is what we use to prove it. But with 16 gauge wire in that transformer, this circuit had a passband response within about half a dB across about 3 to about 14 megahertz, which is just astonishingly flat, extreme flat. And that transformer with the shorted secondary and capacitor could be made into an L network. So experiment with that and see what you get.